Hello, Earth Science students. In this video, I'm going to talk about how water is a polar molecule and how that affects its properties. All right, so a polar molecule is a molecule that has partially positive and partially negative areas on the molecule. And the example of that we're going to talk about in detail today is the water molecule. So it turns out that oxygen atoms, when they bond to hydrogen atoms, they don't share the negative electrons evenly. So the oxygen atoms are kind of greedy, and they keep more of the oxygen atom keeps more of the electron density near itself. And that means that the oxygen side of the water molecule has a slightly negative charge, while the hydrogen side has a slightly positive charge. And these things operate sort of like magnets, where the sides that are opposite charges to each other kind of stick together. Like the positive part of one water molecule would be attracted to the negative part of another water molecule. And it would also be the case that two water molecules probably wouldn't arrange such that the positives were near each other for a long period of time, because they would repel. They would push away like two north poles of a magnet would. So when water molecules freeze in particular, they will line up and they'll actually form hexagons, which is why snowflakes are six-sided, because that hexagonal structure makes its way out into the overall shape of the snowflake. All right, so polar molecules, like water, can dissolve other polar molecules. So that means water can dissolve a lot of other stuff. So water can dissolve polar liquids and solids. Some pretty common examples of that would be alcohol is a polar liquid, sugar is a polar solid, and then lots of ionic solids. Okay, you might be like, what's an ionic solid? Well, it is most of them are crystalline substances. Salt would be an example, that come together from a metal and a nonmetal being bonded to each other, like sodium chloride or potassium chloride, or calcium carbonate or magnesium carbonate, which are the components of limestone. So water is able to dissolve a lot of things, and that means that it's going to be very important for understanding things like streams and rivers, because those streams and rivers are going to, and even groundwater, dissolve the minerals that are soluble in water and carry them off. So that's how you get caverns forming in limestone, and also why the ocean is salty, because those rivers constantly carry all those minerals into the ocean, and when water from the ocean evaporates, the minerals are left behind, and that's why the ocean is much more salty than, say, the Yadkin PD River. All right, sometimes water is referred to as the universal solvent, and that's because it can just dissolve a lot of things. Now, it's pretty easy to see that it's not universal, because the term universal would mean that it would dissolve everything, and then you wouldn't be able to find anything to put it in. So water doesn't dissolve everything, but it does dissolve a wide variety of substances. And you can probably think of some examples, kind of in your kitchen, for example, Kool-Aid powder, salt will dissolve sugar, and maybe like the glass or the countertop isn't going to dissolve in the water. All right, so nonpolar molecules don't have separated positive and negative areas, and so they're not attracted to polar molecules. At least they're not attracted strongly enough to dissolve in them. And so are water molecules attracted to nonpolar molecules? No, water is polar. Well, you can tell if something's nonpolar, or at least one easy test you can do is just mix the two substances together, and if it dissolves in water, it's probably polar, and if it doesn't, if it separates out like vegetable oil, dissolve into water. It just kind of floats on top. Then you can tell that the vegetable oil is a nonpolar molecule because it doesn't dissolve in the water. All right, so some nonpolar substances you might be familiar with. So paint thinner, gasoline, dry cleaning fluid, oil, and wax. All of those things are nonpolar. You might have noticed too that if you go to try to rinse these things off your hands, particularly the oil, I hope you haven't put dry cleaning fluid on your hands. The oil, it's hard to get it off, right? Because it doesn't dissolve in water well. So you soak your hands up really well, preferably before you get the oil on them, or before you put the water on, and then that soap dissolves the oil, and then you rinse the soap oil mixture off your hands with water. All right, so the phrase like dissolves like simply means that polar substances can dissolve other polar substances, and nonpolar substances can dissolve nonpolar substances. But you're not going to be able to get something that's polar to dissolve in something that's nonpolar very well. All right, so some examples. Nail polish is largely nonpolar, and you can remove it with acetone, which is also largely nonpolar. By the way, you probably bought it as nail polish remover, but the active chemical in the nail polish remover is acetone. Okay, so sugar is polar and it dissolves in water, which is polar. Salt is also polar and dissolves in water, which is polar. And oil-based paint will dissolve in gasoline. Latex or water-based paint will dissolve in water, and there's a big difference between those two. And if you're painting something, you do need to pay attention to what you're using. All right, so the properties of water can all be explained by the polarity of water. And I've got a couple of videos that I want you to go out and watch. The links should be in the guided notes. And I'll just go through and briefly talk about them. So adhesion is the property of water where water sticks to other surfaces, like maybe your hand or a paper towel or a leaf after it rains. Cohesion is the property of water where water molecules stick to one another and beat up and form droplets. So you probably noticed, rain falls as drops. If you spill water, sometimes it'll kind of stay together in drops instead of spreading out evenly across the surface. All right, surface tension. And okay, I'll go back and explain. So the polarity of water, adhesion, the water molecules are attracted to the other surface. Polarity of water allows them to be attracted to each other as well. Surface tension, if you ever jumped into a pool, you probably noticed that when you hit the surface of the water that you feel like you kind of have to break through, or maybe you've seen those water strider bugs that kind of run around on top of the water. And you can even take a paper clip very carefully and set it on top of the surface of water, and it'll just sit there until you, maybe knock the glass or something, and then it finally falls down because the metal that the paper clip's made out of is more dense than water, so it should sink. But the surface of the water, the polarity of the water causes the water molecules on the top to attract strongly to each other and kind of make a skin over the water that makes it more difficult to break through the surface. Okay, when water freezes, I talked about how the positive and negative sides of the water molecules line up with each other and sort of make hexagons. Here's a diagram that does a pretty good job of showing that, because you can see the water when it's in a liquid state, the molecules are just kind of randomly arranged, probably more favoring an attraction between the hydrogen and the oxygen. But when it freezes to form ice, you get that hexagon. And that opens up space. So that means when you when water freezes, it gets bigger. That can expand cracks in rocks. It can bust your pipes. If the water line going into your house freezes, it can cause damage to all kinds of other things around your home as well. But in earth science, of course, the weathering of the rocks is probably the most important feature there. Okay, we've already talked in great detail about water's ability to dissolve things. Water has a high specific heat because of its polarity, because the water molecules, since they're strongly attracted to each other, they can absorb more energy before they speed up. And then also the high heat of vaporization. In order to vaporize water, you have to get the water molecules to completely separate from each other, and that means that when they completely separate, you have to break these attractions between the polar parts of the water molecule, and that takes a lot of energy. So that's why water has a high heat of vaporization. All right, so go and watch these videos and complete the guided notes and turn them in, and thank you for watching.